Hello student, good morning. Today we discuss the concept of interference. Now first point is principle of superposition. When a number of waves traveling through a medium superpose on each other, the resultant displacement at any point at a given instant is equal to vector sum of displacement due to individual wave at that instant. Now consider here the two light wave can be travel at a certain medium. Suppose this two light wave is in phase at that time, therefore its amplitude get added. That means A is equal to A1 plus A2. In another case, the two light wave are out of phase. At that time, its amplitude gets subtracted. A is equal to A1 minus A2. Now, if the amplitude of two waves are equal, then for first set of particle, the displacement will be twice the amplitude of individual wave. And for second set of particle, the displacement will be 0. Thus, the intensity of wave, which is proportional to square of amplitude of the wave, will be non-uniform, being larger at some places and smaller at other. This is called interference. In same case, these two light wave are in phase, the intensity is maximum. These two light wave are out of phase, the intensity is minimum. That means the corresponding intensity get maximum and minimum. Now this ray diagram shows the interference for water waves. Consider water waves S1, S2 are sources of water waves of the same wavelength and same amplitude and are in phase with each other. That means at any given instant of time, the phases of the wave emitted by both sources are equal. The crust are shown by continuous circle, while the trough are shown by dash circle. Now according to this ray diagram, S1 and S2 be the two sources. Now this continuous circle indicate the crust and this dotted circle, this indicate the trough. Interference can be divided into two types. The first type is known as the constructive interference and second type is known as the destructive interference. First, what is the constructive interference? Points where the crust of one wave coincide with the crust of another wave and where the trough of one wave coincide with the trough of another wave are shown by blue dots. Here this blue dot indicate the corresponding constructive interference. At this point, the displacement is maximum and is twice that for each wave. These are point of constructive interference. Second, destructive interference. The points where the crust of one wave is coincide with the trough of another are shown by red dots. This red dot, according to this ray diagram, this red dot indicate the destructive interference. At this point, the displacement is 0. These are points of destructive interference. What is the coherent sources of light? Two sources which emits the wave of same frequency having a constant phases difference independent of time are called coherent sources. At any given point in space, at every instant of time, there are light waves from multiple sources overlapping one another. This must be interfering, and we should be able to see interference all around us at all time. We see no interference pattern. This is because different sources emit the wave of different frequencies, and even if they emit wave of same frequency, they are not in phase. Thus, the interference pattern changes every instant of time, and no pattern is sustained over a significant length of time for us to see. Thus, to obtain sustained interference pattern, one usually obtain two secondary sources from same primary source, as is done in Young double slit experiment. Now next point is Young double slit experiment. This is the ray diagram. Now according to this ray diagram, here consider S be the source. This is monochromatic source. Now AB be the slit. Here S1 and S2 be the secondary sources. Here PQ be the screen, and this pattern is known as the interference pattern. Now consider a plane wavefront is made to fall on opaque skin AB having two similar narrow slits S1, S2. The plane wavefront can be either obtained by placing a linear source far away from the screen, or by placing it at the focus of convex lens kept close to AB. The ray coming out the lens will be parallel rays, and the wavefront will be plane wavefront as shown in figure. For simplicity, we assume that the slit S1, S2 are equidistant from source S, so that the wavefront starting from S and reaching the end up to at every instant of the time are in phase. When the ray falls on S1, S2, the two slits acts as secondary sources of light, emitting cylindrical wavelets to the right of AB. The two secondary sources emit the wave in phase with each other at all times. The crest or trough of secondary wavelets superpose as shown in figure and interferes constructively along straight line joining the blue dots as shown. These blue dots. The points where this line meet the screen have high intensity and are bright. Now the center band is always the maximum intensity, means bright fringes. The images of the slit are also perpendicular to plane of the paper. The image plane rotate through 90 degree is shown on right side of the figure. Midway between this line are line joining a red dot along which is crest of one wave coincide with the trough of the other, causing zero intensity and producing dark image of the slit on the screen PQ. Means this band is dark band because the intensity is minimum. There are the dark region on the screen as shown on right. The dark and bright region are called fringes, and the whole pattern is called interference pattern. Now let us take the direction of propagation of the plane wave incident on AB. As x-axis, the screen is along YZ plane. Y-axis being along the plane of the paper, the origin of axis can be taken to be O. The origin is considered the O. The central point S1 and S2 as shown in figure, which shows the XY cross section of experimental setup. Let the distance between two slits S1 and S2 is represented by small d, and that between O and O dash is represented by capital D. In short, small d be the distance between the two virtual sources, capital D be the distance between slit and screen. For better result, D should be about a meter for a slit separation mentioned above. Now let us determine the position of other fringes on the screen. Consider at any point on the screen the two wavelets from S1 and S2 travel different distances to reach point P, and so the phases of the wave reaching P will not be same. If the path difference del L between S1P and S2P is an integral multiple of lambda. Now lambda be the wavelength of light. The two waves arriving this will interfere, the constructively producing a bright fringes at P. If the path difference between S1P and S2P is half integral multiple of lambda, there will be destructive interference and a dark fringes will be located at point triangle S1 dash P and S2 dash P. According to Pythagoras theorem, S2 P square minus S1 P square is equal to D square plus Y plus D divided by 2 whole bracket square minus D square plus in bracket Y minus D divided by 2 whole bracket square is equal to YD. Y be the distance from O dash to P and D be the distance between the two sources S1 and S2. S2 P square minus S1 P square is equal to, solve these brackets, D square plus Y square plus YD plus D square divided by 4 minus D square minus Y square plus YD minus D square divided by 4. Here plus minus D square cancel, also plus minus Y square and plus D square divided by 4 minus D square divided by 4 get cancel. This YD plus this YD, that means 2YD. And how to represent? S2 minus S1 in second bracket S2 plus S1 is equal to twice YD. Rearranging this term, S2 plus S1 gets shifted to right hand side. S2 minus S1 is equal to twice YD divided by S2 plus S1 is equal to del L. This del L indicate the path difference. For D, small d divided by capital D is less than 1. S2 minus S1 is nearly equal to twice d, giving then the path difference del L is equal to 2 into yd divided by twice d. 2 get cancelled, is equal to y small d divided by capital D. Now the condition for constructive interference at point P. Del L is equal to y suffix n small d divided by capital D is equal to n lambda. Here n be the integer number, lambda be the wavelength. For nth bright fringes, value of n is equal to 0 plus or minus 1 plus or minus 2 dash up to etc. Now y suffix n is equal to n lambda d divided by small d. This is equation number 2. Similar for nth dark fringes, n is equal to plus or minus 1 plus or minus 2 dash up to etc. Now S2 minus S1 is equal to del L is equal to yn small d divided by capital D is equal to n minus 1/2 lambda. Yn is equal to n minus 1/2 lambda d divided by small d. Now this is equation number 3. The distance between any two successive bright fringes is equal. This is called a fringe width. The fringe width is represented by W is equal to del y is equal to y n plus 1 minus y1 is equal to lambda d divided by small d. Lambda be the wavelength, d be the distance between source to screen, and small d be the distance between two sources. Thus both the dark and bright fringes are equidistant and equal width. We can also write the equation 1 and 4 in terms of phase difference between the two waves as follows. The relation between path difference del L and phase difference del phi is equal to twice pi divided by lambda into del L. This is equation number 5. The phase difference between the two waves reaching at point P from S1 and S2 is given. Del phi is equal to y small d divided by capital D in bracket twice pi divided by lambda. Now this is equation number 6. For constructive interference, in terms of phase difference is given by del phi n is equal to n twice pi. Now n is equal to 0 plus or minus 2 plus or minus 2 dash up to etc. Now this is equation number 7. For destructive interference, in terms of phase difference is given by del phi n is equal to n minus 1/2 twice pi. The value of n is equal to plus or minus 1 plus or minus 2 dash up to etc. Now this is equation number 8. Now next important point is intensity distribution. As there is constructive interference at the center of bright fringe, the amplitude of wave is twice that of the original wave incident on AB, and intensity I being proportional to square of the amplitude is 4 times of intensity of incident wave is I suffix 0. At the center of dark fringes, the intensity is 0. At in between points, the intensity gradually changes from 0 to 4I0 and vice versa. Thus, the interference fringes are equally bright, equally spaced. This is, however, valid only in the limit of vanishing width of the slit. For white slit, the waves reaching a given point on the screen from different point along a single slit, difference in path length travel and the intensity pattern changes, the resulting in a blur interference pattern with poor contrast. We can calculate the intensity at point P on the screen, where the phase difference between the two waves is phi, as follows. We can write the equation of two waves coming from sources S1 and S2 at point P on the screen as, now the first relation, E1 is equal to E0 sine omega t and E2 is equal to E0 sine omega t plus phi. The incident intensity I0 is equal to mod of E0 square. The resultant electric field at point P will be given. Add these two relations. E is equal to E0 sine omega t plus E0 sine omega t plus phi. Solving this relation is equal to twice E0 cos phi by 2 sine omega t plus phi divided by 2. The amplitude of the wave is twice E0 cos phi by 2. Thus, the intensity at P will be proportional to mod of 2 E suffix 0 cos phi by 2 mod square, and it will be equal to 4I0 cos square phi by 2. Let us consider the case when the amplitude of wave coming from the two slits are different, E10 and E20. In this case, the intensity of bright and dark band will be different from when is discussed above. At the center of bright fringes, the amplitude will be E10 plus E20, and hence the intensity will be proportional to E0 plus E20 square, while at the center of dark fringes the intensity will not be 0 but proportional to mod of E10 minus E20 square. Now next point is condition for obtaining well defined and steady interference pattern. The first condition, the two sources of light should be coherent. We have seen the waves emitted by two coherent sources are always in phase or have constant phase difference between them at all time. If the phases and the phase difference vary with time, the position of maxima and minima will also change with time, and the interference pattern will not be steady. For this reason, it is preferred that the two secondary sources used in interference experiment are derived from a single original source. Second condition, the two sources of light must be monochromatic, as can be seen from the condition for bright and dark fringes. The position of these fringes are as well as the width of the fringes depends on wavelength of light, and the fringes of different color are not coincident. The resultant pattern contains color overlapping bands. In fact, original Young experiment was with pinhole, not slit, and for sunlight producing color interference pattern. Third condition, the two interfering waves must have same amplitude. Only if the amplitude are equal, the intensity of dark fringes, that means destructive interference, is 0, and a contrast between bright and dark fringes will be maximum. Fourth condition, the separation between the two slits must be small in comparison to the distance between plane containing the slit and observing screen. This is necessary as only in this case the width of the fringes will be sufficiently large to be measurable, and the fringes are well separated and can be clearly seen. Fifth condition, the two slits should be narrow. If the slits are broad, the distances from different points along the slit to a given point on the screen are significantly different, and therefore the waves coming through the same slit will interfere among themselves, causing blurring of the interference pattern. And sixth condition, the two waves should be in the same state of polarization. This is necessary only if polarized light is used for the experiment. Now, next point, method for obtaining coherent sources. According to Young double slit experiment, we can use the single source. The single source passing through a narrow slit, and then we can produce the two secondary sources. There are other ways to get two coherent sources. The one of is the Lloyd mirror. This is an extensively used device. The light from source is made to fall at a glazing angle on plane mirror. Some of light falls directly on the screen as shown by the blue lines in the figure, and some light falls after reflection as shown by red lines. The reflected light appears to come from a virtual source, and so we get two sources. They are derived from a single source and hence are coherent. They interfere, and interference pattern is obtained as shown in figure. Here this is the interference pattern. Now here we can show the direct and refracted ray by blue and red lines. The light is monochromatic, having a single wavelength. The second is Fresnel biprism. A biprism is a prism with a vertex angle nearly 180 degree. It can be considered to made of two prism with very small refracting angle ranging from 30 minute to 1 degree join their bases. In experimental arrangement, the refracting edge of the biprism is kept parallel to the length of slit. Monochromatic light from a source is made to pass through narrow slit S. According to this figure, when light passing from this slit S, these two reflecting surface create the two virtual sources. The two half of this biprism from virtual images S1 and S2. These are coherent sources having obtained from the single secondary source S. The two waves coming from S1 and S2 interfere, and from interference fringes like that in Young double slit experiment in shaded region. This shaded region be the interference pattern. Thank you for the watching.